welcome to day 11 of Leetcode 75. We're doing search in a binary search tree. This is problem number 700. And we're given a root of a binary search tree and an integer val. We have to find the node in the binary search tree such that the node's value equals val and return the subtree rooted within that node. If such a node does not exist, we return null. So a tree node, we're using this concept called a tree node, and this is an optional value. So that means that it can be a tree node or it can be null. And we have a class tree node here, which is the definition for the binary tree node. And its constructor contains a value, a left node, and a right node, a left tree node or a right tree node. And the default values is 0. You can have no left children or no right children. Those are the default values. So we're given a function search bst where we have to provide the root and the value that we are searching for. So you have this example here, 42713, and you have, this is just how the this is on a breadth first search how the tree is kind of laid out. So on the first level you have 4, and you have 2 and 7, and then you have 1 and 3. And the value is going to be, so you're looking for the value 2, so you return 2's node 2, which has its left children and right children. And then if you were searching for value 5, you can't find it in this tree because there is no value 5 with any of the nodes. So the number of nodes within a tree is going to be between 1 and 5,000, and the node's value is going to be between 1 and 10 to the 7. The root is the binary search tree. The value is going to be between 1 and 10 to the 7 as well. So a binary search tree is essentially a very useful data structure, which is very helpful for organizing and sorting data points. So essentially it uses a general tree, which is a DAG, which is a directly acyclic graph. So that means that we can never have any cycles within this data within this data structure, and every single node has either a left or a right child. That is how we can denote edges between nodes within this graph. Sometimes within graphs you can have more than 3 edges, but within binary search trees you can only have 2 edges, and those are the left children and the right children. And something very important to note as well is that the left children will always be smaller than the current node, and the right children will always be greater than the current node as well. So you can see that in this example here, you have 1, 2, 3, 4, and 7. 4 is the root node that starts at the top of our tree at depth 0, and then you have the left children, which is 2, the right children, which is 7, and 7 is greater than 4, 2 is less than 4, and then when you go down to 2's children, 1 is less than 2, and 3 is greater than 2 as well. So that is how we can define a binary search tree, and using these properties we're able to search through the tree. So we should try to use recursion when we deal with tree problems. So essentially what we have to deal with is certain conditions, right? So once we hit a root that is null, if there's no tree to search to, we just return null. If the value that we're of the root or the tree node we're looking at is the value that we're searching for, we return that value. Another condition is that if the current root node is the current node that we're looking at, its value is less than the value we're searching for, then we want to look onto the right side of the tree. So we can delimit all of the options on the left hand side, since we said in our properties that within the current root node, if the value the left children have lower values and the right children have greater values than this current root node, and do the same thing on the left hand side. If all of those are false, then if the node doesn't exist, we return null. So let's go ahead and write this out. So if the root is equal to none, then we just return none. If the value is equal to the value that we're searching for. We return the subtree rooted within this node, so we return the actual root. If the root dot, and we can write this in else as well. If the root dot value is less than the value we're searching for, then we want to return a self search BST on the root dot right side. We want to search the right side of the tree, since, as we said again, the value that we're looking at is less than the value of the current node is less than the value we're looking for, so we need to look on the right hand side to see if any of those nodes contain the value that we're looking for, since we know it has to be set on the right side of the tree, since we know that it's greater than the current value we're looking at. Okay, and then we would pass in that value. In all other cases, we return self.search BST on. Actually, we probably cannot do this because that would end all of our conditions. So we'll just do if root not val greater than val is search on the left hand side, and otherwise we'll just return none. And that should be the solution to the problem.